Friends, let's have a look at problem 463, island parameter. This problem is again a problem related to counting the islands or related to the number of islands. So in this video, we're going to explain a solution format and then discuss its variants. First, I'll read through the problem statement to digest the requirement. And then we sketch our plan, and finally we explain the code and do some comments. First, let's look at the problem statement. So we have a grid which has row and column in size, and this grid is binary. If it's 0, it means water, and it's 1, it represents land. So grid cells are connected horizontally or vertically, right? And the grid is completely surrounded by water, and there is exactly one island. The island does not have leaks, meaning that the water inside isn't connected to the water around the island. And one cell is a square with side length 1. The grid is rectangular. Width and height don't exceed 100. So we want to determine the parameter of the island. So here are 3 examples. And in example 2 and example 3 are very special because there's only one land cell and they are surrounded by waters. So the output is 4 because each land cell has 4 edges. In the first example, if you do verbose counting, so the return is 16. So we are going to explain this number when we do the coding. So with that said, that's basically about it for this main statement. We need also to notice these constraints. So now let's explain our plan. So in the first version, we are going to write a solution based on the observation that if a land cell, so here is it means if a land cell site is next to water, its contribution to the parameter is 1, right? And also we can do, this is one way of understanding. Another way is that each land cell has 4 sides, right? And if it's isolated or it's surrounded by all in the 4 directions by waters, then its contribution to the parameter is 4. And if its above cell is also a land cell, and then its contribution is decremented by 2, and due to the 2 edge shadowed. And if its left cell is also a land cell, then its contribution is decremented by 2 again due to the 2 edge shadowed. We could scan the grid left to right and up to down to do the counting, right? So this is another way of understanding. For the second way of understanding, we can also look at below and right cell for the computation. Basically, the point is that we need to fix a order, or an order for the counting. So with that said, let's first write the solution based on the observation that if a site is next to water, its contribution is 1. In this case, basically we just need to check if we are for a land cell is 4 neighbors. If the site next to a water, then we just count its contribution. So now before, because we assumed that the grid was surrounded by water, so we can augment this grid, right? So first let me write m and n. So this is the number of rows and number of columns. So actually this solution can be read in very compact form, but for the purpose of explaining the idea, let's write in some verbose way. So we have this, and first I'm going to do this grid. So I'm going to insert. So here I'm going to insert this one, right? And also I'm going to append another one. So length is m. This way we use the water to enclose the top row and bottom row. Similarly, I would like to enclose the left column and right column. For this, what we're going to do is for I in range, see, currently we have m plus 2 rows, so I have to do this. And then what we're going to do is that grid, we're going to reset its grid I maybe. So it's 0 plus grid I, and then plus 0. So this way, let's print the length of grid and length of grid 0. So here I'm going to minus m minus m. This should print out 2, right? So here let's we insert from the beginning. So yeah, we have 2. Now we are ready to do the counting, right? Let's make some annotation. Step 1. This is the augment the grid. And step 2. So we're going to do the counting. Let's call it step 2. For this, actually, it's very standard. So we initialize a result variable, which is an integer, and then we're going to return its final state. So now let's iterate over the grid. So for I in range, so we can start from 1 and ending at the original column. So that's, we write m plus 1 here. Then for j in range 1, then we are ending at n, right? So we write n plus 1 here. Then we want to check if grid ij is land, right? That is it's 1, right? So if it's 1, then we want to check the 4 neighbors. If the neighbor is a water cell, then we can increment the result by 1. So basically, let's see, grid I minus 1 j. If this is 0, so this is a cell above, right? If this is the water, then we can increment the result by 1. If grid I plus 1, this is the one in below, right? If this is also water, so we are going to increment the result by 1. Now let's look at the left and right. So left is I and j minus 1, right? If it's 0, then we are going to increment this result by 1. Similarly, the right one, j plus 1. If this is 0, then we're going to increment the result again by 1. So this way, we finish the main problem logic. So basically, this part is saying that if we match a land cell, then we are going to determine if one of the edges of it can contribute. The condition is that it's next to a water, right? So now we are ready to do the return. So we just need to return the final state of this result variable. So with that said, let's first do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So this is one way of writing this a solution based on the observation, right? So actually this code is not very compact. You can make it compact. That's a good exercise. So this is the one way. Now let's write another solution. So here I'm going to use this one as V1, right? And then what I'm going to do is that, so basically what we want to do is based on the second understanding. So we want to see, so isolated land cell, the contribution is 4. If we check the above and the left cell, above and left cell, so if there are shadows, so decrement, and contribution by 2. The overall result will be correct. So now let's write this solution, then it can digest. So first we get m and n, the number of rows, number of columns. So here's 0, right? So now let's initialize a result variable that's counting the edges. And then we're going to iterate then for I in range m, right? For j in range m. So I in range m and j in range n. So here m is number of rows and n is number of columns. We're going to check the above and the left cell, basically. Then first we are going to check if this grid corresponds to a cell that is a land cell. If so, first we are going to increment this one by 4. Then we check shadowing, right? So check. So for this, I'm going to look at in this version of solution. I'm going to look at above and look at left. So if I minus 1 is greater than or equal to 0, right? In other words, not out of bounds, and I minus 1 and j is also allowed, right? So in this case, we are not checking the waters like here, and we check the lands, right? If this is the case, so we're going to decrement this result by 2. Similarly, we can check the left. So for the left, we need to check I and j minus 1. So if j minus 1 is greater than or equal to 0 and grade I j minus 1 is 1, then in this case, we're going to decrement this again. So this check actually covers all the cases. So now we are ready to do the return. So we are going to return the result state. So here we get this m and n, but we just use it for iteration. We can substitute this m and n by here and comment out this one, but that's a small detail. So this one is shorter maybe. So actually this one maybe really we can write it as a one-line solution, but that's not our point. So now let's do a check for this second version. This is not right. So let's see. We have I minus 1 and grade I minus 1. If this is 1, we're going to yes. So yeah. So here if j minus 1, so we're going to check grade j. Yes. Let's see here m and n, I range n. If grade ij is 1, so we're going to do this. Oh yeah, so I guess here this is the thing, the indentation. So we need to, if it's 1, then within it we check the shadowing. So now let's check again. Yeah, it passes one example. So because this one passed, then for sure this isolated one must be right. Now let's check. Yeah, now let's look at the generic case. Yeah, it passes all the cases. So here, let me make a comment. In this one, I look above and look left. So actually, we can look below and look to the right. So let me copy this part. Let me maybe copy all the code to explain another format. I'm going to use this one as version v2. And then here, let's look down and look right. So here we keep this line and we keep here. And then if the grid is a land cell, we increment the result by 4. Then we check shadowing, but we look at the one below. So if we want to look at the one below, we want to check if I plus 1 is in bound, right? So here we are going to check j plus 1 if it's in bound. So for I plus 1 inbound, so we need it to less than the number of rows, that is m. For j, we want to check it less than n, right? Then the same thing. This will be a variant of the second understanding. So now let's do a check. It passes this one, but this one is so special. Now let's look at this example 1. Oh yeah. Now let's look at the generic case. Yeah, it passes all the generic cases. So I would see that the version v1 and is 1 based on counting the nearby voters by checking voters, and the version v2 and its variant is based on counting shadowing, right? So within version v2 and v3, so we see that we can look above and look left, and we can look down and look right. Actually, the above and below, left and right, are relative, right? Essentially, they are the same solution, but we need to be able to reasoning on this. So with that said, I guess that's about it for this problem. This one is easy but interesting one. Thank you.